So TAs are there. Megha, Souvik.
Yes, sir.
What about Amar? I haven't heard from him. Amar, Amar. Okay, I'll talk to him anyway.
Hello, sir.
Yes, is it Amar?
No, sir. Like some people have sent request for
Oh yes,
joining
yes.
the.
Mega will approve it. Mega, why don't you approve this?
Yes, sir. I am
Yeah,
approving it, sir, right
yeah.
now.
He's approving. Don't worry. Okay. Parallelly, he's approving. So fine. Anything else? Okay. Fine. So let's start. Okay. So yesterday, if you remember, we have this. Well, let me first share the PPT and then we'll start. My voice is clear, audible. No, no issue.
Yes, sir.
Okay, perfect. Yeah. So yesterday, if you remember, uh, we have talked about, in a very general sense, about the thermodynamics. That what is thermodynamics, what we are going to cover, why it is so important, and we have seen the timeline of various laws of thermodynamics. And ultimately, we came to know that this whole thermodynamics is inspired from the nature. Okay, various people in the various corner of the world have different observations. Okay, and then ultimately, these all observations can be combined very nicely in the form of these three laws. Okay, so that is the overall. You can say, if you recall that last lecture, that was the conclusion of the last lecture. Just to summarize that what we are going to cover in thermodynamics, anyone can try. Maybe okay, Bhavna, you can try. What are the three goals? Well, the three major goals which we are going to cover in this subject.
So spontaneous means we
Yeah,
will discuss
feasibility,
about
feasibility. Yeah,
feasibility,
yeah.
and
Then
we will discuss about means
heat work interconvertibility. That how heat can be converted to work, work to
conversion
heat.
of heat into water and
Yeah,
vice versa.
yeah, and vice versa. And yeah, the last one,
Equilibrium.
equilibrium. Okay, so we
Equilibrium
yeah.
process, yes.
Yeah, so first two topics will be covered by me, and the last topic, which is actually equilibrium thermodynamics, that will be covered by Professor Gargidas. Okay, our ex-HOD. Okay, so let's start today from this first law of thermodynamics. As you can see, I have put this animation. I haven't put the reference. That's not a good idea, but anyway. Acha, Savik, you start recording the lecture. Okay, Savik.
Yes, sir, it has been
Yeah,
started. Sir, it
no,
has been
perfect.
started, sir.
Yeah. So, as anyone can easily infer from this animation, that what I'm trying to convey. Anyone from this animation, what you understand? How it's related to first law of thermodynamics?
We are converting
Conversion.
one
Yeah,
form of
so
energy
energy
to another.
conservation, right? That one form of energy going to another form of energy. Well, here everything is mechanical and bit potential also. Potential to kinetic, kinetic to potential, and so on. Anyway, I mean, this is not directly related to thermodynamics, but just to motivate you that you already know that first law of thermodynamics is nothing but energy conservation. But you will see that in thermodynamics, we'll elaborate on few things which you haven't heard before, or maybe you have ignored that thing, or maybe you haven't gone so deep in first law of thermodynamics. Okay. So before that, just a small introduction about system and surrounding. You know it already. But anyway, system is nothing but it depends on the user or the person who is analyzing, me, you, whoever is the observer. Okay, you can define your own system. Okay, so basically it's an imaginary boundary within which you will observe the changes or you will observe the phenomena. Okay, and rest is surrounding. Okay, and the boundary which defines your system It's system boundary. So it's not a big deal, that you know already. Anyone has any doubt about system? I think it's clear. Anyone? I think it's more or less clear. If any, I will wait for few seconds. If anyone has any doubt, he can interrupt. Otherwise, I mean, it's a very straightforward thing. Okay, so system is clear. So system is an imaginary boundary. Within this boundary, we want to analyze the phenomena. What are the changes within that boundary? Whether it's a change in property or whatever is happening. Okay. And rest is surrounding. And in thermodynamics, mainly heat and work, they cross this one boundary. That's how we define heat and work. We'll see in detail. Okay. And with this transfer of heat and work, remember both heat and work are known as energy in transition. Okay. Because this is energy transfer. You can transfer the energy to the system either by heat or by work. We'll see what is heat. It's an interesting story. So when you do this transfer of heat and work, you change something, you change some property, and that property is called energy, E. So from now onwards, remove this concept of what you know as internal energy. That is one part of energy. Say it energy. Okay. Energy is a property, a state property. It depends on the state of the system. So in thermodynamics, we're mainly going to deal with that how with this work and heat transfer, we can change the property of the system, which is called energy. Okay. Property is defined for a state. So what about heat and work? Heat and work are energy or what? I am saying that we are going to change the energy of the system, right? Or we are going to change the property of the system, which I am calling energy. And how we are going to do it? Heat and work. So what do you think, Sahil, about heat and work? Are these energy? Form of energy? Sahil?
Yes, sir.
Are heat and work energy?
Sir, I think heat is a form of energy because of
And work,
vibrations in the molecules.
work.
Sir, I think work is a output of energy.
So,
If we put energy, we will get
keep
work.
these confusions in your mind. Simply remember, heat and work are energy, but in transfer. Okay.
Yes, sir.
Through heat and work, you cannot accumulate energy. You can transfer the energy through these two quantities, heat and work. So remember, heat and work are energy in transfer, whereas energy, the symbol E, is the energy of the system. Okay, a system possesses that energy. Okay, so all are energy, but two are in transition. You can transfer the energy either by heat or work. Okay, so there should not be any confusion. Okay, let's go ahead. So on this slide, what you should remember is that we are talking about property of a system, which I am calling energy, and this property can be changed either by transferring energy through heat or through work. So heat and work represents the energy in transition. Okay. Well, this you can read that both heat and work are boundary phenomena. Their transfer always happens at boundary. Okay. Remember, system possesses energy, but system cannot possess heat and work. Through heat and work, you can transfer the energy. So unlike properties, heat and work has no meaning at a state, right? These are path functions that you know already from your JEE preparation, that these both are path functions. Whereas energy, capital E, is a state function. Earlier you were knowing it as only in the form of U, right? Jagadish, you are hearing me?
Yes, sir.
Yeah, so you remember that in JEE you used to know this U, right? Internal energy, right?
Yes, sir.
That dq is equal to du plus dw. That's what you were knowing, right? Now get rid of this U. Remember E. Internal energy is a subset. Total energy is more generic. We will see why. Great. So you will see that mainly we are going to talking about heat interaction, work interaction. How we know what is heat? How we know what is work? Either of course, from intuition one can decide But then there should be a formal way to define whether we will call some energy transfer heat or that energy transfer is a work interaction. When you are transferring energy to the system, it can be heat or it can be work. But how we will decide whether it is in form of heat or whether it is in form of work? We will see. Feel free to interrupt me. Okay. Let's go ahead. So first, let's talk about energy. So energy means what? That property which we are talking. And why I am saying property, that will be clear very soon. You have to wait for the whole story. Okay. So this energy includes K, kinetic energy. When I am saying kinetic energy, I am talking about macroscopic kinetic energy of the system. What does mean by microscopic kinetic energy of the system? So I have given an example that let's say if a gas is trapped in a cylinder with a piston, and if piston has some mass, okay, and if piston is moving with a finite piston has a finite mass, and if it is moving with a finite velocity, and if its velocity is changing, or even if its velocity is not changing, if it has some velocity, that is called macroscopic kinetic energy. Okay, Rishabh, does it make sense, this kinetic energy?
Yes, sir.
Yeah. Can you give any another example of such macroscopic kinetic energy?
Might be anything such as
A
free falling.
ball is falling, simple. Right?
Yes,
Free fall.
sir.
So its
Free
velocity.
fall.
So that is called macroscopic kinetic energy. Okay.
Yes, sir.
Okay. Okay. So I'm not going to define everything. See, in thermodynamics, the best way is that imagine the examples rather than defining everything. Don't define everything. There is no need to define formally everything. It's better we understand from the examples of the nature. Okay. So 2 examples I have given you. That is called macroscopic kinetic energy. Okay. Then this energy includes potential energy. Now, this potential energy can be any kind of energy. Okay. Mostly we talk about gravitational, but it can be elastic energy also. Okay. If your system has a piston with a spring, and this spring is getting compressed or elongated, then you have elastic energy stored in the spring. So that is potential energy. Okay. Then we are coming to internal energy, which you know from your school education. Okay. This internal energy is, so remember, internal energy is a subset of total energy. So when you did it in your 10+2 education, these first law of thermodynamics, you ignored other energies. You ignored K, you ignored P, and you ignored something else which we are going to see. That is called others. I tell you what is others. So U is nothing but, in a very broad sense, it's the overall molecular kinetic energy, or what we call it microscopic kinetic energy. It's not a good word, microscopic kinetic energy. It's a microscopic picture. The better word is, it's a overall kinetic energy at molecular level. And that you know that every molecule, either it's a solid or gas or any phase, these molecules contain either translational or rotational or vibrational or all three, all two. So so this is nothing, this is called internal energy, right? This is the overall molecular kinetic energy. And what is the source of this? Like anyone, from where it comes? Can anyone throw some light?
Temperature.
Yeah, so basically it's from the Brownian motion, right?
Yes, sir.
Yeah, so it's whoever said it, it's due to the temperature. That whatever temperature, accordingly these molecules have, you know, random motion. That what we know as Brownian motion. So this and then they can rotate also, they can vibrate also. So that is known as internal energy, right? And then lastly we have others. In others I include everything. It's chemical energy, it's nuclear energy. Let me give an example. Let's say a salt is kept in a container. Okay. And if I'll ask you what is the, and let's say my system is that container, including salt. If I'll ask you what is the internal energy of your system, then you have to calculate the chemical, that bond energy of NaCl also. That will be your internal energy. Let me give you another example. When you were, I think, in your school education, I mean, in 10+2, when you were doing this, I think, chemical reactions. When you do this, when you try to find out the heat of reaction, the way to heat of or heat of formation, whatever quantities you calculate, how you do it, that you know the bond energies, summation of bond energy of reactants and summation of bond energy of products. Okay, and that's how you calculate the heat of reaction. Why heat of reaction is important? Because if some reaction is going on in a container, and if you want to know how much heat has been released, and probably that heat can be used in some process, some thermodynamic process. So in that sense, this chemical energy comes in the picture. So remember, internal energy also includes the chemical energy. Okay, so basically, let's say if you start with A molecules, okay, and these A molecules react with B, and it makes C and D, and in this process, if heat is getting released, so your initial internal energy, internal chemical bond energy of A and B molecules, and your final internal energy is chemical energy of C and D molecules, and if something is left from A and B, and if you when you take this when you subtract these internal energies, you get the how much heat has been generated in that thermodynamic process which is reacting. So chemical energy is also included in this energy, that we'll see in chemical reaction chapter. Okay, thermodynamics of chemical reactions. Similarly, it can be nuclear energy also. If some nuclear process is going on, nuclear fission or fusion, then that energy, and that you have already seen when you I don't know whether you have done it or not, but remember that when you try to calculate the energy in a nuclear reaction, then you do this delta mc square. Okay, so that is basically delta m is nothing but the loss in mass of nucleus. Okay, so that is nothing but let's say some A element, and after fission it makes B. So when you want to calculate the heat of that nuclear reaction, you take the energy of nucleus of B molecule minus energy of nucleus of A molecule. So you can think this way, that your initial internal energy is nothing but the nuclear energy of A element, and final energy can be, if it's only nuclear energy, for nuclear energy of B molecule. Okay, so overall gist is that this energy includes everything: chemical energy, nuclear energy, molecular kinetic energy, potential energy, kinetic energy, all this. Okay, of course, whatever problems we are going to solve, at least non-reactive thermodynamics, in most of these cases we are going to ignore K, P and others. The reason is that one reason can be the processes are very slow, so kinetic energy mostly we ignore. Potential energy may not. Sometimes we will consider this potential energy. And what happens many times that this other changes are so significant that with let's say change in U or change in P, with respect to that, if change in K is very small, we ignore it. Okay. But anyway, whether we'll ignore or we will not ignore, that depends on the problem. But up to this point, everything is clear. I'll wait for a minute. That energy includes all these energies. If you have any point to comment, or if it's clear, then we'll move. Fine. Okay. So we know that what does mean by energy of a system. We have seen the various component of energy of the system. Okay. Now let's talk about what is heat. Okay, what we will call heat. So now we have talked about energy. Now we'll talk about heat and work, and then again we'll revisit all these three quantities through Joule's experiment. So if you'll see the history of heat, if you'll go before Joule, you will be amazed that how people define it. That it's an invisible, orderless, massless fluid, which was called caloric, and this fluid, invisible fluid, always flows from hot to cold body. Today, it may sound a bit awkward and that what kind of definition it is, but that's how people were treating heat. Believe me, before Joule, you can read the history. Okay, so before Joule, people were the whole scientific community was believing that it's an invisible, odorless, massless fluid which flows from hot to cold body. Okay, and heat is a substance that could not be created and destroyed. But today we know that it's completely wrong, because we can generate heat by just simply rubbing our palm. Okay, by doing work, you can generate infinite amount of heat. So it's wrong that heat cannot be generated and cannot be created and destroyed. You can create heat by work. If you rub your palms, by doing work, you are creating heat. Okay. So remember, Joule has to fight a lot to establish the first law. We'll see soon. But before him, that's what people were believing, that it's a fluid. Okay. But of course, it is wrong. I have given this example. Okay. Of course, the top statement is also wrong, that it's an individual odorless fluid. Okay. It doesn't make any sense. By the way, before Joule, that's what people were believing. And the unit of heat was, that's why it's called calorie. Okay. But today we know, and that is the correct definition, which I have written at the bottom part, that heat is defined as the form of energy that is transferred between two systems or system or surrounding. Okay. It's saying surrounding is also a system, remember. So heat is defined as the form of energy that is transferred between two systems or system and surrounding by the virtue of a temperature difference. Remember. So that is the only key point. You will say that energy transfer is heat if there is a temperature difference. Otherwise, no. So thus an energy interaction is heat only if it takes place because of a temperature difference. So that is the formal definition of heat. To identify or to recognize whether a energy transfer is heat or not, that is the only key. And if something is not heat, it is work. Remember. That's how you can identify. So first try to identify whether an energy transfer is heat or not. And what is the key? There should be a temperature difference between that two systems or system and surrounding. And if we find it is not heat, then it is work. We'll see an example. Not an, we will see 2-3 examples to understand this concept. So remember, on this slide, we are defining formally heat. We discarded the old definition of heat before Joule, what people were thinking. And it's not very, I mean, Joule has conducted his experiment in 1848 or 43 probably. Before that, that's what people were believing. And if something is so strongly established in scientific community in those days, when most of the places, the form of ruling was monarch, there was a king. You remember destroying, or shatter these established concepts, it's not easy. If you'll see from a scientist point of view, it was very difficult for Joule to establish the correct thing that we will see. Okay, so we talked about heat, that's how we identify heat. Now let's talk about work interactions. So before we go to this slide, I'd like to interact with a few of you. So let's talk with Nidhi. You can hear me?
Yes, sir.
So can you give an example of work?
Yes, like moving fan or moving person, any kind of work, mechanical.
No. Any kind of mechanical work. Remember, so you are saying mechanical work. So you have defined one kind of work, mechanical work. Okay.
Yes, sir.
Well, I'll make it more. Any other example you can think? Anything? A piston movement. Right?
Yes. It
So
is
in
also,
most of your JEE problems, there was always a piston which is moving, right, by a gas, right?
yes, sir.
So you are familiar with that work, which you also say PV work, right? Yeah. So that work is defined as boundary work. So let me share this slide with you. Boundary work means boundary is moving. Okay. So in work interaction, first kind of work is mechanical work. Okay. And in mechanical work, The first type is system boundary movement by excess force. Remember, this excess force is very important. If there is no opposing force, no work. So spend some time here. Okay. System boundary movement against the opposing force, or of course by excess force, you can say. If there is no opposing force, there is no work. So that's why I made it like I have put a star there. That must be opposing force. So this is called, many people say it PV work. I call it boundary work, boundary movement work. Okay. Another form of mechanical work, you can say work done by elastic or restoring forces. For example, you see this work done by the spring or on the spring. Okay. Then another form you can see is another restoring force, which you know as surface tension force. Okay. When you try to pull a fill, you are trying to overcome the surface tension forces. This example you have seen probably in your JEE. That's how you define surface tension, force per unit length. You try to pull this wire against this film. Film is trying to pull the wire towards itself, and you are trying to pull it towards yourself. And you maintain the equilibrium so that the force applied by it just equal to the force applied by the film. So this is also kind of restoring force. So their work is done by surface tension forces. That is also mechanical work. Another example you can think of mechanical work is, if you remember this Young's modulus experiment, if you take a solid rod, it should be a bit elastic, and if you hang some mass, gradually it extends. So there also you define Young's modulus, and then Young's modulus is nothing but a manifestation of spring constant, and then accordingly you can calculate the work done. Okay, so these all forms are, these all things are come under the umbrella of mechanical work, either spring work or surface tension force work, or this work done in elastic solid, or this PV work. Okay, so let me see. Rakesh, you can hear me? Rakesh?
Yes. Yes.
So is it clear that mechanical work, it can be what kind of work we are talking about?
Yes, sir.
So surface tension work is clear to you? If there is some system where surface tension forces are there, we also call it capillary force. Is that concept clear?
Yes, sir.
Just explain us.
What?
How we'll calculate work done by surface tension forces. So let's say if I tell you the surface tension, let's take this example. Let's take this example here, which you see on the slide. Let's say I tell you that surface tension is gamma. Okay. So if surface tension is gamma, and if it's a film, and let's say if you extend it by a distance, small distance x, what will be the work done by the external agent or work done by the surface tension forces? You are doing it very slowly so that at each point there is an equilibrium. Yes. So Rakesh, what is surface tension? How we define surface tension?
What, sir?
How we define surface tension?
Surface tension. Force per length.
Force per unit length, right? Not per length, per unit length. So what is our length here? L, right? So gamma into L will be the force, right?
Yes, sir.
And you have two surfaces, so you multiply it with 2. So gamma into 2L. You know the force, you know the displacement. You can calculate the work.
Force.
Right? Simple.
Displacement.
Okay. Yeah. So that is called mechanical work. Now I think someone, Nidhi or someone, has given an example of fan. So remember, was it Nidhi who has given the example of fan?
Yes, sir.
So Nidhi, that is called soft work. Okay, that is mechanical work, of course, but that is another category. It's called soft work. Okay.
Okay.
So basically, if you take the room as a system, and then if there is a fan which is crossing the boundary of the room, then whatever work will be done by this fan, that will be called soft work. Okay.
Okay.
Another kind of work you will see turbine work, pump work. Okay, these are all soft work. Wherever something is rotating by the fluid in the system, or that equipment is rotating the fluid of the system. Fluid can be air also. That is called soft work. So what happens in turbine? Why we call it soft work? Anyone knows what is turbine? Yes, Muskan, you have some doubt? Muskan, I can see you have raised the hand. Muskan? Hello?
No, so by mistake it happened.
No problem. Okay, now since I have called your name, can you, Sneh, you have some doubt? Sneh Bandhu Singh?
Yes, sir. Sir, I want to ask, if there's a container with a plate which is movable, but the plate is massless, and
In that case, of course, we if so, then you have to see piston is massless. Fine. So yeah, go ahead.
and if there's vacuum out,
So yeah, I'm going to discuss this example. Okay, that's why I first time your question doubt is right. So just keep it with you. Okay, I will come back to you.
yes,
Okay?
sir.
Yeah. Okay. Before that, first let me clarify this soft work. So maybe whom I should talk? Muskan, you can hear me? Since I was talking to you, let me ask you. So do you know what is turbine, Muskan? If not, then I'll tell you. No problem. Because we are discussing soft work, so it's a good time to discuss what is a turbine.
Yes, sir.
So what is the purpose of turbine?
Sir, through mechanical work, we generate like electricity.
Yes, you are right. So that's what.
Like
So electricity.
water
So
falls
basically,
on the
air,
turbine.
fluid, or steam, whatever it turns the turbine, right? It rotates the
Yeah.
turbine. So that is also soft work. Okay.
Yes,
Their
sir.
soft work is done by the system fluid. On the other hand, when fan is rotating in your room, there is soft work done by the equipment on the fluid. Got the point? Okay.
Yes, sir.
So if something is rotating by the fluid, or something is moving the fluid by rotation, that is called soft work. Okay, this much understanding is clear. Let's move ahead. Good, thanks. Okay, now we will come back to what Sneh said. So Sneh had made a very good point. See, I have made a star that there must be opposing force. And Sneh was saying that, let's say, sir, there is a piston which is massless. There is a gas trapped in a container. There is a piston. Piston is massless, and there is no atmosphere. It's vacuum. So what will the work done by the gas? So Sneh, now you answer. What do you think? According to this definition, the way we defined this boundary work.
According to this, it should be 0.
0, because if there is no opposing force, there is no work done. Remember, that's how thermodynamics works. We cannot prove it. We know it from intuition. I mean, from various examples. If there is no opposing force, gas doesn't lose any energy at all, if we ignore the friction and all other things. So remember the way you define work done integral
Sir.
PdV. Yes, please.
Sir, according to me, that process is happening because there is an increase in entropy. Means because of
That's fine,
expansion.
but we are not worried about entropy. I got your point. Why it is happening, I am not interested right now. Okay. I'm not interested in the reason. I'm interested in the I am trying to find out the answer. What is the work done?
Work done would be 0.
Yeah,
There
there
is no opposing force.
why? Because we are see the many people may get confused that work done is integral PdV. So why work done is 0? Remember, integral PdV is valid if each moment you have equilibrium. But if you have a gas inside a chamber, and if there is no gas outside the chamber, if it is a vacuum, then there is no single point where your system is in equilibrium. So you cannot define integral PdV. And we'll see example. Remember, whenever you want to calculate the work done by your system fluid. Acha, who said entropy? Sneh, you said, right? Someone said that
No, sir, it
entropy.
was Ayush.
No, sir. I said
Who is it? Just tell the name.
Ayush.
Ayush, just throw some light. We'll come to that point, but since you discussed, I want you to comment on that. So what is that
Yes,
your entropy point? That entropy
Sir,
of the
but-
gas is increasing, right? Yeah, true.
Yes, sir.
Yeah, that's why it expands. Of course.
Yes, sir.
But so that is one point. That is a truth. I mean, that is a one fact. Another fact is work done is zero. That's how we define it in thermodynamics. Okay. Yes, please. Whoever is it, your voice is. Voice is breaking. Come again. Your voice is not clear.
Am I audible now?
Yeah, now it's fine. Yeah, tell me.
Was zero in the previous case, the example given by Sneh was due to two reasons, I guess.
Yeah,
It
yes.
was not.
Please. I think your voice is breaking. Can you pass your answer to someone else, or you can type and then we can discuss? Can you type it? Because your voice is breaking.
Yeah.
So meanwhile, she's typing. So here I am sharing a very important concept, and you will confront in all the problems which we are going to solve, almost all the problems. Whenever you want to calculate the work done by the system fluid, means whether it's a gas or something else, or steam or vapor, whatever it is, always see the opposing forces. If you can calculate the work done against those opposing forces, if you'll sum them, that's all. We'll see through example. And never remember integral PdV. This integral PdV may work, may not work every time. But if you do it, if eventually we'll see that whatever integral PdV we say, that works for particular cases, and that also comes out to be that work can be written as the sum of the work done against those various opposing forces. We'll see through an example. So remember, whenever you want to calculate the work done by the system fluid or by the system, what you call, try to see the opposing forces. If you can calculate the work done against those opposing forces, if you will sum them, you are done. That's how you should do. Then there will not be any confusion. And example will make it more clear. And that's why if there is no opposing force, there is no work done. It doesn't matter how, whether gas pressure varies according to ideal law or any other law, doesn't matter. Yeah. So is there, have you written your point? Let me see. Chat. No, I think Bhavna who was speaking. Work done was zero due to two reasons. One is massless piston, two is vacuum, right? What if piston is not massless? See, Bhavna, if piston is not massless, then piston mass is itself an opposing force, right?
Yes, sir.
So in that case, there will be some work done. I'm saying there should be some opposing force. Okay. If you include a piston also in the system, then it will appear as a form of change in potential energy. See, let's discuss it a bit carefully. So if you consider only gas in your system, right? And Bhavna, if you can write yes or no. When I will say after the final answer, if you are convinced, you can say yes, convinced. Okay. If you take gas in your system and not the piston, then piston mass is an opposing force, and then there even if there is vacuum, I said there is should be some opposing force. Then the opposing force will be the weight of the piston. Yes, this point is clear.
Yes, sir.
Okay, perfect. Let's go to another example. Same problem. If you include the piston in the system, in that case, how this work will come in the picture? Then it will not come through work because you included the piston in the system. Then how it will appear? Anyone, or maybe Bhavna or anyone else? How this change is going to appear in my calculations?
Potential energy should be
Yeah, so it
considered.
will come through E, and within E we have PE. Very good. Okay. So that's it's clear, right? That it's not only vacuum, or it's not only it can be any opposing force. Even if it's vacuum, if there is a piston, of course, if it has mass, you have to consider it. Okay, we can move ahead. Yes, Bhavna, clear? We can move ahead. Okay, thank you. Okay, chalo, let's move ahead. So we are done with mechanical work. We have seen most, I mean, that's what we confront in thermodynamics: boundary work and shaft work. Okay. Now let's talk about non-mechanical work. And these all are work, remember. So that there is something called electric work and there is something called magnetic work. I will tell you electric work, and then similarly then you can see the magnetic work also. Electric work means what? You see on the right hand side, what is happening, that there is a heating element, okay, connected through a voltage difference. So there is a resistor. So what will happen when heat will flow through this wire or heating element? It will get heated, okay, and then it will supply the heat to the chamber if gas is kept in the chamber. Okay. Now, whom I should ask? Let me see. Anyone interested? I mean, any volunteer to discuss with me? Anyone? And then I'll start discussing, because I need someone to interact. It's interesting.
Yes, sir.
Yeah, who is it?
Shivai.
Sorry, come again. What's her name? This
Shivai.
Sivoy. Sivoy.
Yes.
So Sivoy, now tell me that so since we are heating this element, and that whatever is inside the chamber, that is getting heated, what you will say, whether it's a heat or work? What do you think?
So the wire is getting, the temperature of the resistor will increase, and
Very good.
that energy will transfer through heat.
So you are saying it's heat, right?
Yes, sir.
Okay. Now, very important point. As whether something is heat or work, that depends on the choice of the system. So you are saying gas is your system, not the heating element, right?
Yes, sir. The wire is the system and other is
No, wire is not in the system. If you include the wire in the system, remember, okay, then wire is
Yes,
in the
sir.
system. Then see, heat, what I said, heat and work, these phenomena always occur at the boundary. If you include heating element in the system, then heating element is inside in the system. So there is no heat transfer at the boundary. And then it becomes work. Now one can argue how it becomes work. Because if you see, if this square box is my system, and this heating element is inside the system, through this wire electron will cross. And that's
Okay,
why we say it electric work. Now, just to make it more clear, let's go here. Same example. Depending on what is your system, choice of system, it will define whether you will call it heat or whether you will call it work. If it's heat, very simple. That's what Siva explained us. If it's work, then we'll call it electrical work. Okay. Remember, these are not going to change our answers, but from conceptual point of view, it's important to define things properly. Okay. So on the left hand side, Siva, you can see the left hand side.
Yes, sir.
Yes. So here you will call it heating of an oven by work transfer, because your heating element is the part of system. Okay.
Yes, sir. Got it.
Yeah. So we always define heat and work at the boundary. If there is nothing happening at the boundary, it means if heating element is inside the system, you cannot say it's a heat. So then what logic we will say? That these wires are crossing my system, through which current enters in the system.
Electron is.
So this electron is crossing the boundary, and that's why it's called electrical work, not heat. Okay.
Okay, sir.
Same problem. if someone chooses the system what you did earlier, that if only gas, you see that I have seen this by this dashed line. If on the right hand side, if you take that as a system, then heating element has a higher temperature and the gas has a lower temperature or atmosphere in the oven. And since energy is passing from hot element from higher to lower temperature, there is a temperature difference between the system and surrounding, right, Siva? Because this time system is only gas, right? And heating element is in the surrounding because it's not the part of the system, right?
Yes, yes.
So that's why we can say it heat.
Yes.
That's all. It's not going to change our answer. The only thing that either it will appear in work term or heat term, its value is going to remain same. Okay. So this example defines, yeah, thanks. What is heat and what is work? Anyone else has any doubt regarding heat and work?
Yes, sir, I have doubt.
Yes.
Means,
Yeah, please.
sir, the point is that the transfer of energy means in this there is a heating element. So the transfer of energy is due to the temperature difference between the two. So how can you
Between the two,
classify them?
what is that two? What is that two? Tell me. How we
So
define
like
it? Let's
if
go
we
to
have the
definition of-
heating element,
Let's go to the definition of heat. Read this statement. Between the two systems or system and surrounding. Okay. What are your two systems? If you take
electric
heating
oven and electric rod.
so then you have two different systems, na? So one is system, one is surrounding.
Yes, sir. So
So
that
that's
is
what I'm
heat.
saying. Yeah, that is heat.
And sir, what about work? Means
No, if you include that heating element inside the system, okay,
yes.
then whatever is happening, you cannot say it heat. See, it's who is it?
So sir, how can we say it is work?
It's just a matter of definition and convention. Like, you know, just we are properly defining it. That's why I see at the end of who is it? Just name and then I can address you properly.
Ayush.
Ayush, the point is that it's not going to change your calculations. Okay. See, you have see what the problem is that we have our you know, we are already biased with the our understanding of heat, which may not be correct, because we never have you ever tried to define properly what is heat from your school days? Never. This is the first time you are seeing that how we should define it. Okay.
Yes, sir.
Since our mind is so much prejudiced with this thought that if something is getting heat and if it is transferring that heat to some another element, it should be heat or another system. But whether something is heat or not, it depends on the choice of the system. And I agree with you that it's just a matter of definition. Okay. At the end, if we do the calculation, that term will appear in the form of some number. Doesn't matter whether you call it work or you call it heat. At the end, it's the energy transition, right, guys?
Okay, sir, I understand your point. Like in the first one, in which we have heating element in the system boundary,
yeah,
there is a transfer of electron from external source.
Yeah, that you see, that also we are saying to convince ourselves. Believe me, it's just a matter
Yes,
of.
sir, I have a doubt here.
Yeah.
Like we are saying it work by the logic that electron is moving.
Yeah.
Right. Sir, but work can be done like when there is a force and then displacement. So the system has not getting any displacement.
Oh well, that again, if we go to the fundamental, like some good books of thermodynamics, they say that don't remember this very limited definition of work done is that mechanical definition, force into displacement. The more generic, and I will share that page with you from YVC Rao. So it is written that you should think work as some driving force, some force field, and in place of displacement, some another kind of change like dq. Ayush?
So, but what is the use of classifying it? Matlab,
No, there is no use. No.
Is it
Okay,
it is not having any significance as such.
Yeah, that's of course I agree with you. But the point is that when you are establishing a course to teach it, when you are formalizing things, then you have to define it properly, right?
Means it is all about energy transfer.
It is all about energy transfer. That's what I'm trying to convey. That doesn't matter. I mean, you can define your own thermodynamics. Anyone can define. It's just a matter of definitions. We are sticking with one particular kind of definition. It may not be true. You may not get convinced. You got the point. That just in order to formalize things, what is heat and what is work, there is so much discussion. At the end, if an engineer is calculating that how much power I require to heat the oven or to cook something in the oven, ultimately numbers will appear, right, Ayush?
Yes, sir.
Whether you call it work or heat. So that's something. Don't get into these definitions very deeply. Just under some definitions, we are classifying it. As you said, there is no significance at the end. The significance is only getting marks in the exam, that I'll twist the problem and I'll say whether it's a work or heat. Otherwise, there is no use. Believe me. Yes.
Yes.
As an engineer, in practical life, all matters is calculation. Okay. But that is also important to know that, okay, if someone defines the heat and work in a particular manner, then that's how we decide whether something is work or heat. Okay. And as you said that the formal definition of work done is F force into displacement, then how this VdQ becomes work. So again, people have extended the definition of work also, mechanical work, that rather than saying it force into displacement, say some kind of force field into some kind of change, displacement kind of change. It can be DQ or so. You are right. I agree with you that there is not much significance. Okay. Okay, great. Good that you guys realize this, that at the end we are just following some great guys who just define how we should, what we should call work, what we should call heat, like the pioneer of thermodynamics subject. Okay. Very quick example, you can think over it and then we'll leave this lecture. Okay. Joule experiment will, okay, one important point. So let's stop the lecture. We'll see this example, reversible process, in the next class. I'll upload this slide. You can go through this slide, reversible process. Just think over it, what I have written, and then we'll come back to this. It's very important.